Assalamu alaikum students. Let's continue chapter 11 and we have lecture number 4 for this class. In previous lecture we study about the ideal vapor compression cycle. So in this class we'll continue. Let's try to solve the related problem to the ideal vapor compression cycle. Now uh, consider a refrigerator uses refrigerant 134A as a working fluid and operates based on the ideal vapor compression cycle. And that cycle operates between the pressure 0.14 and zero point 0.8 megapascal. Basically, the vapor compression cycle operates at one is the high pressure and the other one is the low pressure. Sorry, low pressure and high pressure. Low pressure is the evaporator and the high pressure is the condenser after the compressor. And the mass flow rate of the refrigerant is 0.05 kg per second. Now, based on this given data, calculate the rate of heat removal from the refrigerated space. So, this is basically the heat extraction capacity. We can also calculate in terms of kilowatt as well as tons of refrigeration. And part B is to calculate how much is the input required for the compressor, then the heat removal, heat rejection in case of condenser, and then the performance of that refrigerator in terms of coefficient of performance. And then the second part is what happens to COP if throttling valve is replaced with the isentropic turbine. So we have to compare the performance of the same refrigerator if the expansion take place with the help of isentropic turbine as compared to the throttling valve. So first of all, we need to, this cycle is based on the ideal vapor compression cycle. So you know in ideal vapor compression cycle, 1 to 2 is isentropic compression in compressor, then heat rejection in the condenser at constant pressure, and then the isenthalpic process 3 to 4, and then the cooling effect, I mean the heat absorption in the evaporator. Now in part B, we have to compare that instead of 3 to 4, which is isenthalpic process, what is the performance of the cycle if we use an isentropic turbine for the expansion, right? So let's first solve this problem based on the ideal vapor compression cycle and the throttling valve. So to calculate this, we can start from the state 1. So we know at state 1, we know this is the one pressure range and this is another pressure range. So the bottom one is for the evaporator and the top one is for the condenser with 0.14 megapascal and then 0.8 megapascal. So at state 1, what are the known values? We know the state of this. This is dry saturated and we know the pressure 0.14 megapascal. So that means pressure is known to us and we know H1 is equal to Hg. So we can calculate that enthalpy as well as we can read the property. And that refrigerant is 134A. So the properties of this refrigerant are given at the end of the book. I have provided the property table as well. I'll email you again that property table if you don't have. Now, um, then from state 1 to state 2, we know this is S1 is equal to S2. At state 2, we know the pressure. That pressure is 0.8 megapascal as well as S2 is equal to S1. To know the state, we know two independent intensive properties. So then H2 we can calculate, then state 3. At state 3, we know this is saturated liquid and we know the pressure 0.8 megapascal. So H3 is equal to HF, which is equal to 95.47 kilojoule per kg. Then at state 4, this is an isenthalpic process. That means H3 is equal to H4. So state 4 simply because of the throttling process, H4 is approximately equal to H3. So the same enthalpy at state 4. So now we know all the enthalpy. State 1, enthalpy at state 1, enthalpy at state 2, enthalpy at state 3, enthalpy at state 4. So now we can calculate all the unknowns. Let's start from the first unknown, which is to calculate the rate of heat removal from the refrigerator space. So this is basically the refrigerated space 4 to 1. So the heat removal, that means HQL is equal to H1 minus H4. So H1 minus H4 times the mass flow rate of the refrigerant. So we can put that value. So that value is equal to 7.18 kilowatt. We can also convert this in tons of refrigeration by dividing with 3.51 kilowatt. So then you will get tons of refrigeration. But net, that's not required in this problem. And the part B is to calculate the power input to the compressor. So the power input to the compressor, this is the compression process. So that means H2 minus H1 times the mass flow rate of the refrigerant. So we can calculate this. That's equal to 1.81 kilowatt of input is required for the compressor. So then part C is to calculate the rate of heat rejection, which is in condenser. So 2 to 3, that means H2 minus H3 times the mass flow rate of the refrigerant. So if you put that value, that means 9 kilowatts. So that means one part of the heat is absorbed in the evaporator, then one heat as a result of the compression. So both heat has to rejected in the condenser. So the sum of this and this should be equal to this one, the heat rejected. And then finally, the performance, that COP of this cycle is equal to the heat removed, which is also called the cooling effect, that heat absorbed in the evaporator divided by the input. So if we put that value, that's equal to 3.97. That's the COP of this cycle, right? Now in part 2, it says what happens to COP if the throttling valve is replaced with the isentropic turbine. So in that case, I mean, this is the expansion using 3 to 4S is the expansion using isentropic turbine. So that means we have to calculate that value 4S. In that case, we are going to use S3 is equal to S4. So that means we know the pressure here. Pressure is 0.14 megapascal and S3 is equal to S4. So using this formula, first of all, since this S4 is in a mixed region, so that means we have to use, first of all, we need to calculate what is the value of X4. So how we normally calculate X4? We can calculate this S4 is equal to SF plus x4 times sfg. So from here we can calculate the value of the x4, and then we can use the same formula for the enthalpy, like h4 is equal to hf plus x4 times hfg. So from here we can calculate the value of h4x. So remaining is the same. Now, what's the value of the heat absorption now? Now, the heat absorption will be from 4s to 1 now. That means now the cooling capacity is increased, because previously the cooling capacity was from 4 to 1. Now, the cooling capacity is from 4s to 1. That means more heat is absorbed by the same cycle. Similarly, as a result of the expansion of the turbine from 3 to 4s, we can get certain work output from the turbine. So as a result, the work input to the turbine will be reduced now, because we are getting some work output from the turbine. So now the turbine output will be H3 minus H4S times the mass flow rate of the refrigerant. So 0.33 kilowatt is now the output from this cycle. So now the input will be reduced. So the input to the compressor is decreased from 1.81 kilowatt to 1.48 kilowatt, because this we have to minus from this one. And similarly, the heat removal, I mean this one, heat removal in the now it is increased from 7.18 to 7.51 kilowatt. So that means the cooling capacity is also increased. What about this COP? COP of the refrigerant would increase from COP is equal to the QL divided by the input of the compressor. So now the new COP is equal to 5.07. So that means an increase of 28% as a result of the replacement of the that throttling valve with the turbine. But the problem is this is not practically feasible because to replace a valve, throttle valve is just a capillary tube, and the cost of that capillary tube is in rupees. It may be like 500 rupees, maybe maximum 1000 rupees. But if you purchase a turbine, expansion turbine, the cost will be in thousands. So that means the initial cost is increased, but the output is very small. You can see 0.34 kilowatt, that output is very small. So if we compare the input cost for the turbine, and moreover, the expansion in the turbine take place in the mixed region. So that means the life of that turbine will also be very small. So that's why, although theoretically using a turbine we can get higher COP, less input to the compressor, but the problem is the cost of the turbine as well as the life of the turbine, right? Next, we'll discuss heat pump system. Normally, in our uh, household, we are using air conditioner. Air conditioner normally is used to produce cooling effect, is used to produce comfort. Basically, heat pump and the air conditioner, they have the same component. And same component mean both have two coil. One of the coil can be evaporator, another can be the the that reject the heat outside, what we call that. One is the evaporator and the another one is um, forget the name, evaporator and condenser, sorry, that's the condenser. So we can use the same equipment for the air conditioner as well as heat pump. The only difference will be that, let's say this is our indoor coil. Indoor coil mean that fan will throw that air in inside the room, from this to inside the room. So that's the indoor coil. So that indoor coil can act as an evaporator as well as condenser. It depends on the direction of the flow of the refrigerant, because after that compressor, after the compressor, the coil we named it as a condenser. So this is the, if this is the direction, then this is compressor, then this is condenser. So condenser mean heat is rejected to the environment. So here we'll get heat, right? If this is the arrangement, we'll get heat, right? But if we use a reversing valve, that reversing valve can change the direction of the flow of the refrigerant. So let's say the direction of the flow of the refrigerant is now this one. Now after the compressor, the coil is condenser. Now this indoor coil, the same, this coil is acting as evaporator now. So in that case, evaporator mean it will absorb heat from the room, so that refrigerant will absorb heat from the room, or in other word, this is a cooling coil. This is a cooling coil. So the fan will throw cold air into the room. So by using a reversing valve, we can use the same equipment for the air conditioning as well as for heating purpose. We just need an additional reversing valve. With the help of that control panel, we can change the mode for heating, cooling. So basically what we are doing, we are using that reversing valve, we are giving signal to that reversing valve that now we want the cooling inside the room or we want heating inside the room, right? Now that heating purpose can be achieved with the help of like air, atmospheric air, in our local domestic air conditioner or heat pump. Basically, we use atmospheric air. That's the air to air system. But sometimes we can also use the water source. Water source inside the earth, sometimes we have warm water or sometimes we have condensate. So we can use that condensate to, let's say we have condensate, so that condensate can give its heat, or warm water, it can give its heat to that refrigerant. So that refrigerant will take that heat, and additionally because of the compression, another heat, so that heat can be given to the room, right? To that room. So the source of heat can be, I mean other than the heat from the atmosphere.